Okay, so today we're going to talk about the Darboux Criterion. So what this is essentially an alternate, you can think of it as an alternate definition for Riemann integrability, or you can just think of it as, or what it really is just an equivalent condition for a function to be Riemann integrable. So first, we've already showed that a Riemann integrable function is bounded. So when we go through these proofs, we're going to assume that with our function f is going to be bounded, because we can kind of deal with that. If we have an unbounded function, then there's no point in dealing with proofs about Riemann integrability because it won't be Riemann integrable. Okay. So with this in mind, we can define some special constants for our function. Well, I guess they're not constants. So what we're going to do is let P be a partition, and I'm just going to abbreviate this by part. Be a partition of our interval AB. So remember, this is a selection of strictly increasing finite sequence of points starting at A and ending at B. And so we are going to define these numbers. So capital M sub I is going to be the supremum of f of x on the interval x sub I minus 1 to x sub I. So this is one of the intervals of our partition. And similarly, we're going to define little m sub I to be the infimum of f of x, where x is in the interval x sub I minus 1 to x sub I. So this is telling us sort of the bounds for f of x on some interval, okay? Or on an interval of our partition. So we're going to start with a lemma before we prove the Darboux criterion. Oh, actually, no. We have one more definition. So, or I guess one pair of definitions. So we are going to let u of f and p. This is going to be called the upper sum of f with respect to p. And it's going to be the sum over the partition of capital M sub I times delta xi, right? So notice that this kind of mimics a Riemann sum, except that instead of f evaluated at some point on the interval, you're replacing that by the supremum. And similarly, we're going to let L of f and p, so this is the lower sum of f, is going to be the sum of little m sub I times delta xi. So by construction, since sort of little m sub I is less than or equal to f evaluated at some point in the interval from xi minus 1 to xi, so this inequality is true for any evaluation points that we choose, because they come from this interval. So we have that the lower sum is less than or equal to the Riemann sum of f with respect to some evaluation points. I think, yeah, I'm supposed to put set stuff over here, and this is less than or equal to the upper sum we have, right? Because every piece of the sum is going to be sort of the form f of x sub I, and since it's bounded by that, we get that inequality. It's pretty straightforward. Okay, so now we can move on to the lemma. And the lemma states that if P and P prime are two partitions of the same interval, AB, then the lower sum of f with respect to P is less than or equal to the upper sum of f with respect to P prime. So no matter what partitions we choose, upper sums essentially are always going to be bigger than or equal to lower sums, even when you're looking at the sums with respect to different partitions. So this is actually a very, at face value, this is a very non-trivial result. The proof isn't too complicated though. So we're first going to consider what happens when we add a point to our partition P. So consider what happens when essentially P prime is equal to P union with some point, and that point is not in P already, right? So we're adding a new point to our partition. This means then there is unique k such that, right? This means that z is going to fall in one of our partition intervals. And of course it can't fall on the endpoints because the endpoints are sort of part of our partition. Since z is not in the partition, it can't be equal to one of the endpoints. So we can write this as an open interval. Now, the idea is that in P prime, right, little m sub k prime is going to be the infimum of f of x, where x is in the interval x k minus 1 to z, right? Because z is now, normally this is xk minus 1 to xk, but z is in between, right? Z is creating a new interval for the partition P. And similarly, k plus 1, m sub k plus 1 prime is the infimum of f of x, where x is in the interval z to x sub k, right? And what we can sort of notice by definition is that m sub k prime and m sub k plus 1 prime are greater than or equal to m sub k, right? You can kind of reason that one of these will be equal to m sub k, but one of them can't be smaller, because if one of them were smaller, that would sort of create a contradiction, because essentially, right, I'm just splitting up the interval and then looking at the infimums over those two intervals. I shouldn't get a smaller infimum when I do that, right? I can only get equal to or bigger. And so more precisely, right, the m sub k is going to be the lesser of these two values, right? But we don't need that. Similarly, we can look at big M sub k and big M sub k plus 1 primed, and these are going to be less than or equal to big M sub k, because if I break up the partition and then look at the supremums, I can't get a bigger supremum. It wouldn't make sense, right? And you can give a full-fledged argument if you want to, but I'm just going to save time. It should be immediately obvious. So now when we are looking at sort of u of f p prime minus L of or let's see, what do they do? Essentially, the only difference in these sums, right, is going to be for the term delta xk, right? So we have to look at what is little m sub k delta xk. So this is m sub k times xk minus xk minus 1. And we can sort of introduce the z term like so. Right, so we're just adding and subtracting z. That's a perfectly good algebraic operation. And now we can split it up like this. Okay, so now we know that little m sub k is less than or equal to both m sub k prime and m sub k plus 1 prime. So this expression, I can use that inequality here and here, and I will get m sub k prime times xk minus z plus m sub k plus 1 prime z minus... Actually, I think I should have this the other way around. Yeah, I should have this the other way around. Like that. Okay. And so this is equal to m prime k plus 1 times delta x k plus 1 is prime plus m sub k prime delta x k prime. Okay, so this shows when I pass from sort of the lower sum with respect to p, it's going to be less than or equal to the lower sum with respect to p prime, right? So, oops, I didn't mean to do that. Thus, delta, L of f with respect to p is less than or equal to L of f with respect to p prime, right? Because every other term in the sum with L is going to be the same except for this term here. Because everywhere else you have the same intervals, you have the same m sub I values. And we already know that the lower sum for p prime is going to be less than or equal to the upper sum for p prime. And so this is what we wanted to show, right? But remember, we're doing this in this sort of special case. So how are we going to do this in the general case? It's actually not too bad from here. So Let's see. Oh, we can also show that in the same previous example, sort of by a similar logic, right? If we look at m sub k delta xk, just using a similar idea, breaking up delta xk, and then using the inequalities between m sub k and the prime versions, we get that this is greater than or equal to m sub k prime z minus x sub k minus 1 plus m sub k plus 1 prime xk minus z. So, so essentially what we have is that L of fp is less than or equal to L of fp prime, which is less than or equal to u of fp prime, which is less than or equal to u of fp, right? So this is saying that in the upper sum for p has to be bigger than or equal to the upper sum for p prime. So essentially this says that if I add a point, the lower sum gets bigger, and if I add a point, the upper sum gets bigger. Sorry, if I add a point, the upper sum gets smaller, right? So now let p and p prime be any partitions. So I'll just write parts. Then p union p prime, which we'll set equal to p double prime, is a partition given by adding finitely, right? Partitions are finitely many points to either p or p prime, right? Therefore, if I start with p, right? If I add points, I can add points to get to p double prime. I know that when I add points, the lower sum gets bigger. Okay? And I know that the lower sum is going to be less than or equal to the upper sum. Okay? But now, if I add points to p prime, then the upper sum gets smaller, right? So this is going to be less than or equal to u of fp prime. So we get the inequality that we want, right? L of fp is less than or equal to u of fp prime, where p and p prime are arbitrary partitions. Okay, so I guess I've spent more time in this lemma than I wanted to, but I'm still I'm considering if I should save the proof of the Darboux criterion for another time. Yeah, I think I will, just for the interest of time. So yeah, that's it.